This is the talk which I gave to the BMLA meeting in Solihull in May 2026, and it's entitled Determining the Optimum Fluences Required to Irreversibly Destroy Hair Follicles Using Numerical Analyses. And I have nothing to disclose. So the first thing we should discuss is what the real targets are when we're trying to destroy hair follicles. So back in the olden days, I used to think it was just the stem cells in the bulge, which is located in the upper part of the follicle. And then later I realized that the dermal papilla is actually a very important target. This is the nerve center of a follicle. It sends out the signals to make the follicle grow and then subsequently die, I suppose, when it goes into the catagen phase. Now, the dermal papilla has no chromophore which we can target using light, but it is surrounded by matrix cells, and these cells include keratinocytes and melanocytes, which generate the keratin required for the hair shaft and the melanosomes required for the colour of that hair. And this collection of cells, the matrix cells, they grow in size and in absorption coefficient as the concentration of melanin increases as the whole bulb descends towards the subcutis. So this is actually an excellent optical target, because not only is it dark with all that melanin, it's also quite large compared to the size of the hairs. And here we can see a picture from some microscopy of the papilla surrounded by the matrix cells. Now, as the bulb descends, the whole structure grows in size. This is during the anagen 3 stage, and the matrix can grow to something like 3 times the diameter of the hair shaft itself, while the concentration of melanin within the matrix can be up to 5 times greater than the concentration in the hair. So it really does give us an excellent optical target. So I generated some numerical models. Firstly, a light transport model using Monte Carlo simulations, followed by the heat generation model, and then finally the Arrhenius thermal damage model. So the first step was to look at where all the light energy goes in the skin. So we used Monte Carlo for this. In fact, I used 2 different Monte Carlo engines to compare. And I generated a model of the skin, which was 7 layers, including the stratum corneum and the epidermis, the papillary dermis, the reticular dermis, and the subcutaneous tissues, and input all the scattering and absorption coefficients of all those layers, plus the anisotropy and the refractive indices for those different layers. So what controls the absorption of light energy in the skin? Well, wavelength has a significant control in terms of penetration, as we just saw with those 2 images. The melanin concentration, both in the epidermis and in the hair itself, and particularly in the matrix cells, controls the total amount of absorption that's going to go into the hair. And then finally, the tissue depth. So as the fluence propagates through the skin, it drops significantly due to scattering and expansion of the beam, etc. And so as you get deeper into the skin, the fluence drops quite significantly. And here we see the distribution of fluence in the skin. On the left-hand side, we've got the fluence map for the alexandrite, wavelength 755 nanometers. And we can see that it's quite intense, down to a depth of about maybe 1.5 to 2 millimeters deep, which is not so deep. That's really where the anagen 1 follicle reaches the total depth of anagen 1. The fluence does extend down to 2.5, as you can see there, but it's dropping off now. and it definitely drops off to quite relatively low levels by the time it gets down to anagen 3 at about 3.5 millimeters deep. With the 1064 YAG wavelength, though, you can see that the Fluence definitely transports more energy to deeper layers compared to the 755. This is exactly what we would expect to see for 1064 compared to 755 nanometers. So we can see that both of these are for a 10 millimeter diameter spot at the skin surface. So we can see that the distribution of the energy is quite significantly different between these two wavelengths, as we should expect. Where does all that light energy go? Well, this is a representation of 4 different wavelengths from 532 up to 1064 nanometers. And we can see here the amount of light that's transmitted through the model. Now, by that, what I mean is it can be transmitted outside of the zone of interest. So it can go laterally to the sides, or it can go deep to below the 10 millimeter baseline that we use for this particular model. That's all the blue stuff, and you can see it's quite a lot of light, particularly in the 1064 wavelength. We lose about 55.6% of the light just purely through transmission. This is because the dermis is highly scattering, so the light enters and scatters almost immediately, and depending on the anisotropy, which is wavelength dependent, and depending on the where the light is scattering out towards it, if it's going out towards the side, for example, then we can lose energy fairly quickly. The backscattering, though, we can see here is also significant. That's the orangey bit in the middle, and we can see that at 532 nanometers we can lose up to 55% of our incident energy back through the skin surface out into the local environment. And then we can see that as you go down to or up to the 1064 nanometer wavelength, then that backscattering element drops to about 38%, more than a third of the light. So it is a significant loss of energy. I call this the Jaffa zone. Very little energy actually is absorbed in the tissue, as you can see here. Just over 14% of the 532 nanometer energy is absorbed in tissue somewhere, but the Alexandrite diode and YAG laser wavelengths all relatively small because of the first of all the low absorption in the dermis, and because of the highly scattering effectiveness of the dermis as well. So once we know where the light ends up, we can then calculate the amount of heat that is generated from that absorbed light. And obviously, the higher the absorption within the tissues, the greater the heating. So this is the interesting picture. As the matrix cells increase in both number and in terms of content of melanosomes, etc., the optical target increases in absorption coefficient, and we can see here that for 3 different wavelengths, 755, 810, and 1064, the absorption increases quite dramatically. At 2 millimeters depth, the bulb or the matrix cells essentially don't exist. The follicle is still in anagen 1. But when it gets into anagen 3, this is when melanogenesis kicks in, and when the bulb starts to increase in absorption coefficients. And that will increase as the follicle descends to the subcutis, and as the follicle goes through to the anagen 6 stage rather. So we can see here that at the beginning of A3, the matrix is only about 3.5 millimeters deep, and the absorption coefficient is pretty low. But by the time it gets down to 7 or 8 millimeters depth, it's significantly greater. Now, there's a couple of interesting points here. If the skin is thin, say it's only 4 to 5 millimeters thick, then the bulb descends into the subcutis and at some point stops growing, and therefore the hair stops growing, or the diameter of the hair stops growing, and the matrix size and colour stops growing as well. So this means that superficial hairs, which are located in a thin dermis, will not have as big a target, an optical target, as deeper hairs, because they continue to grow, and the matrix continues to grow with them and becomes darker with them too. So in actual fact, deep hairs present us with a larger, darker target compared to superficial hairs. The other interesting fact here is that when the hair follicle goes into catagen, the matrix cells die very quickly, within 48 to 72 hours apparently, and therefore the optical target disappears. This is why we cannot kill the follicles when they are in catagen and telogen, because there is no absorbing targets surrounding the dermal papilla anymore. It's completely gone. The papilla it has no target. We can't heat it directly. We can only heat it through diffusion from the hot surrounding matrix cells. So this is a very interesting graph because it gives us a clear insight into how the processes change with the growing, expanding matrix, and with the darkening of that matrix with more melanosomes. So the interesting thing here is that as the matrix cells and the dermal papilla descend towards the subcutis, the size and the darkness of that, or the absorption coefficient of the matrix increases, as we can see here, whilst the fluence drops, because we know that as the fluence decays as you go deeper into the skin. So we get this almost like a balancing effect where the drop in fluence is like compensated for by the increase in the size and absorption coefficient of the matrix, and so we can figure out that the optimum depth at which the matrix is killable is somewhere from late anagen 3 to somewhere near the anagen 5 part of the process, but that depends on the on the dermal thickness, not the the other way around. So this tells us that we can kill these certainly the dermal papilla if we get it at the right time and it's not too deep. But if the skin is too thick, then by the time it reaches the anagen 6 depth, which could be as far as 7 or 8 millimeters deep, then the fluence at that level will be too low. We also have to consider that by the time you get down to that thickness, the dermal papilla is essentially encased within the subcutis tissue, the fatty tissue, and the subcutis has quite a different set of optical parameters compared to the dermis. It scatters many more times than the dermis does. This indicates that the anagen 4 stage is the best target for us. If you calculate the what I've called the selectivity index, which is the ratio of essentially the absorption coefficient of the matrix relative to the absorption coefficient of the stratum basal, then we can see that by the time the matrix has descended to the A4 stage and enlarged in size, etc., then it's around about 66 times more selective than the stratum basal. So it becomes an excellent target, but we have to remember that the fluence at that depth is also significantly lower than at the stratum basal. So we have to then calculate whether or not the sufficient energy can reach that depth, be absorbed by the A4 matrix cells, and generate sufficient heat for a sufficiently long period to kill the cells properly. So the next stage in this model is to look at the Arrhenius damage equation and calculate whether the cells can be irreversibly denatured. Now, typically when we look at this, we calculate the value of omega, which is the volume of cells denatured, and normally a lot of researchers will set omega to 1, which is approximately 63% of the volume of those cells. I don't particularly like that as a metric. I prefer to use an omega of 4.6 because that then is equivalent to 99.9% of the volume of the cells denatured. And I specifically chose that omega 4.6 at the base of the dermopapilla, not at the top, because you've got a little bit of a distance there to consider too. So if we can achieve that criteria, omega equals 4.6 at the base of the papilla, then we can say with great certainty that those cells are fully denatured irreversibly, and that follicle is then dead. This table shows the fluence range that my models calculate. So we can see, for example, in the upper lip, the papilla depth is somewhere between 1.5 to 2.5 millimeters. The fluence at that depth has dropped from the incident fluence at the skin surface to somewhere between 30 to 45% for those corresponding to those depths. And therefore the fluence we need to fire at the skin surface to ensure an omega of 4.6 is between 12 and 16 joules per square centimetre. Now, these are relatively shallow follicles, they're not too deep, so they're quite easy to reach. So you should always get a good response. This is with the Alexandrite 755 nanometer wavelength. And then as we go through the various different body targets, so the chin, the axilla, the bikini, lower legs, thighs, and chest and back, we can see a range of fluences which correspond to the dermal papilla depths and the drop in fluence. So clearly what this shows is that as we target different sites across the body, we must use different fluences to account for the thickness of the skin, the depth of the papillas, if indeed that's our goal. So all of this is all done purely from modelling. Needs to be confirmed with proper clinical testing at some point. How deep are the target follicles? How can you tell? Well, a rule of thumb is that the thicker the hair, the deeper the follicle, because the follicles keep growing both in length and diameter as they descend towards the subcutis. The diameter stops growing once it's ensconced into the subcutis, but that might be up to 3 millimeters deep. So they can they don't just stop at the boundary between the dermis and the subcutis. They can keep growing deeper into the subcutis itself. So some key insights. It appears that the optimum time to kill the papilla is when it's approaching or adjacent to or within the dermal subcutis boundary, because the backscattering effect of the subcutis is quite significant, and therefore a lot of fluence that goes into the subcutis will be reflected or rather scattered back up towards the dermis. So the point at which the papilla reaches the boundary will have enhanced fluence compared to the more superficial regions. Most of the thermal denaturation occurs long after the pulse width. The pulse width really is fairly trivial. It's not so important in terms of the denaturation of the target cells. It is important when we're talking about the epidermal layer, of course. We don't want to damage the epidermis, so we need to use longer pulse widths in that situation. But in terms of the actual destruction of the dermal papilla, the important thing is the temperature time history around the papilla. So it's not the maximum temperature, it's not the duration of the pulse width, it's the combination that's important. And it turns out that if you increase the fluence, then you automatically increase the peak temperatures, and therefore the actual denaturation time drops significantly. It's an exponential dependency based on the Arrhenius equation. So in actual fact, it turns out the fluence is king in all these matters. Once you have a sufficient fluence applied to the skin, the pulse width really becomes pretty trivial. Excuse me. And the papilla heating, because the papilla doesn't absorb energy directly, the heating comes from diffusion of the heat generated in the surrounding matrix. So we've got this nice dark matrix full of melanin, and it warms up as it absorbs all that energy, and the heat then obviously spreads outwards into the surrounding tissue, but also inwards into the papilla. So it's kind of like cooking a chicken in an oven, I suppose you could say. But that only happens if the matrix is sufficiently melanized, and that seems to be from late anagen 3 to anagen 5, as long as it's not too deep. In terms of practical guidance when we're actually treating these things, you need to ensure that you are applying sufficient fluence to reach the target depth. That's why it's important to check the thickness of the hair. If it's thick, then it's most likely a deep follicle. If it's thin, it's more likely to be a superficial follicle. So that's a good guide to help us determine the right depth and therefore fluence. But if you're firing high fluences at the skin, you must use cooling to protect the epidermis, because particularly with 755 nanometers, you will get a significant amount of absorption in the epidermis too, and therefore potentially high temperatures. I've got another talk which I'm giving at the same meeting, which talks about cooling to a little more extent and the pulse width effects there too. So we use pre-cooling to essentially balance the fluence, and if you do that correctly, then you'll definitely minimize epidermal damage, whilst ensuring you still get sufficient fluence down to the papilla to achieve good clinical outcomes. So if we look at the cooling, I did a little calculation here. We can see that if you apply ice packs to the skin surface for 30 seconds, then the dermal epidermal junction, which is the purple line here, the temperature of that will drop from about 37 degrees to around about 4 to 5 degrees after 30 seconds. Whereas the bulb, if you've got a relatively superficial bulb at 2.6 millimeters, it only drops to about 20, 27, 28 degrees, while the dermal subcutaneous boundary only drops a few degrees. So applying the ice packs to the skin surface really has a minimal effect on the temperature of the dermal papilla. But in actual fact, it doesn't really matter if the papilla also becomes cold, because it's surrounded by a nice rich sphere of, not a sphere, of melanosomes, which will absorb a lot of energy and therefore generate nice high temperatures around it. So pre-cooling the hair or the dermal papilla is not actually an issue at all. Computer models are always a bit dodgy, and it's easy to generate a whole bunch of complete garbage data, so it's a good idea to try to validate them in some way. And so I did this by using two different Monte Carlo models with two different simulation engines, just to be sure they were giving the same figures. And what I found was that the results converged quite nicely at the anagen 4 depth, so that gives me some confidence. But all computer models have limitations, and we have to acknowledge that. The first limitation is that we have to apply a very simple geometry. We just cannot recreate real geometry in a model like this. There's always some degree of uncertainty in terms of the optical properties of the various layers, and there's always going to be some sort of a biological variability which we cannot really account for. So the data that the results that this model or these models generate have to be taken with the understanding that there's always going to be some variability around the numbers. But the conclusion is that we can use models to calculate optimum fluences based on both the physics and the biology, but they really must be tested clinically to be sure that they actually make sense. Now, knowing that, knowing the sort of clinically applied fluences we do use today, I can say with a high degree of certainty that my model results are actually pretty reasonable. Thank you for listening to this. This is the QR code for my blog. If you want to find out more information about the kind of stuff that I do, please have a look at the blog. I hope you enjoyed this talk.